Winter weather can bring the most beautiful scenery to Iowa. It can also be the culprit behind scenes like these, the ones that you, as an Iowa Department of Transportation snowplow operator, worked so hard to prevent. The use of de-icing chemicals, abrasives, and snow fences to help keep Iowa's roadways safe for winter travel will be covered in this video. Terms like brine and pre-wetting will become a part of your everyday vocabulary, and you will learn how salt lowers the freezing point of water and why it is such an effective tool in the Iowa DOT's winter storm fighting arsenal. It wasn't many years ago that a 50-50 mixture of rock salt and sand was the primary formula used to combat snow-covered icy highways. Today, advanced materials technologies and methods are providing many more options for effective and cost-efficient application of de-icing chemicals and abrasives. Both anti-icing and de-icing techniques are becoming highly refined. That is because of the greater selection of de-icing chemicals, improved application equipment, better trained personnel, improved weather forecasting, and roadway weather information systems data. But before we go further, let's define anti-icing and de-icing. As the term anti-icing implies, it is taking measures prior to a precipitation event to prevent the formation of a bond between precipitation and the pavement by timely application of de-icing chemicals. In other words, anti-icing is a proactive weather-fighting measure. On the other hand, de-icing is a reactive measure to break the bond that is formed between the ice and the pavement by chemical or mechanical means, or a combination of the two. With each approaching winter storm, you may want to first consider an anti-icing strategy. It can pay off handsomely through savings in material, equipment, and labor. Research has shown that it is 10 times more expensive to de-ice than it is to take anti-icing measures and keep precipitation from bonding to the road surface. Anti-icing may not be the best answer in all locations at all times. Check with your supervisor to determine if anti-icing is suitable for your area. But before we get into the methods, let's talk about the de-icing chemicals and abrasives you may be using, where they come from, how to store them, how they work, and how to apply them. We'll start with sodium chloride, a mineral we commonly refer to as salt, rock salt, or road salt. And although it has been around for a long time, salt is still the chemical most used as a freeze point depressant on Iowa highways. Freeze point depressant. Where does that term come from? For now, just remember that all the de-icing chemicals we use on our roads are freeze point depressants. Later in this video, you will learn why they are called freeze point depressants and how they work. Sodium chloride, or salt, is by far the most economical de-icing chemical available. For most winter storms in Iowa, sodium chloride is very effective in melting ice and snow, and it requires no cleanup. However, salt is corrosive to vehicles, needs moisture to work, and is ineffective at very low temperatures. Most of the salt used on Iowa roads comes from mines near Hutchinson, Kansas, or mines in Louisiana. It is crushed, screened, and treated with an anti-caking agent before it is transported. Barges bring the Louisiana salt to Iowa, where it is stockpiled along the Mississippi River. Rail and truck transportation is used to transport salt direct from the mines or from the river stockpiles to Iowa DOT garages across the state. Salt is stored at Iowa DOT garages in sheds and domes. It should be ordered, delivered, and put under cover well in advance of the winter season. To store salt, use a loader to move the salt into the shed or dome, filling from the back and working your way out. An auger or conveyor can be used to completely fill a dome by building a cone of salt in the center of the structure. For details about safe material handling practices, composition, and quality, ask your supervisor who has specification and material safety data sheets for salt and all other de-icing chemicals. Salt should be mixed with abrasives as a conditioner to prevent the sand stockpile from freezing and keep it workable during the winter. There are many ways to mix salt and sand. One way is to use a loader to move a quantity of sand out into an open area. Some garages use motor graders to do the mixing. A 10% salt mix, 1 loader bucket of salt, and 9 loader buckets of sand is a good mix when using salt as a sand pile conditioner. For road use, the percentage of salt you use in salt-sand mixtures will vary depending on what you are trying to accomplish. Let's take a minute to talk about the use of sand as a roadway treatment, either alone or in a mix with salt. Sand provides short-term but immediate traction. But it is not a de-icer. Sand has absolutely no melting effect on snow or ice. In fact, there is some indication that the addition of sand slows the melting action of salt when used in a mixture. Sand at first glance appears to be environmentally safe, but you may want to take a closer look. Sand on the roadway is pulverized by traffic and is a recognized contributor to air pollution. Because of this, sand is banned from roadway use in some parts of the nation. Sand clogs drains and waterways and builds up on roadsides, requiring expensive removal and disposal. Sand is also responsible for chipped paint and cracked or broken windshields on travelers' vehicles. Sand is visible when applied and is generally accepted by the public. It is not temperature dependent, so it is most useful to increase traction when low temperatures make de-icing chemicals ineffective. Your supervisor will recommend when a salt-sand mix should be used. Now, back to the mixing. Once you have added salt to the sand in the proper proportion, mix the two together with a loader. After thoroughly mixing the materials, move the mix back into a pile or into a shed to assure containment. Anytime you are working with salt, you should be aware of environmental issues. Mixing should always be done on a paved surface. When a salt-sand mixture contains more salt than needed to keep the sand pile from freezing, normally more than 10% salt, the mixture should be in covered storage, and there should be dikes to contain any runoff. Calcium chloride, often referred to as chloride for short, is another chemical used as a freeze-point depressant. Calcium chloride is found in natural brines that are pumped from beneath the Earth's surface. It is packaged as pellets or flakes in the dry form or in solutions of various concentrations. Calcium chloride is more expensive than sodium chloride, over 6 times more expensive, and is highly corrosive. But it is effective at temperatures lower than sodium chloride and can continue working below zero. Calcium chloride actually generates heat when it dissolves into a brine, a very beneficial characteristic for melting snow and ice. It also draws moisture from the air, providing water for initial brine formation, which is beneficial in cold, dry conditions. In addition to taking moisture from the air, calcium chloride takes moisture from everything it touches. It takes the moisture right out of leather, which can destroy a pair of gloves or boots in a hurry. When working with calcium chloride, you must always wear protective clothing and rubber boots. Although sodium chloride and calcium chloride are the most widely used de-icing chemicals, there are a number of others such as calcium magnesium acetate, magnesium chloride, and potassium acetate that can be effective in special situations. In addition to being used as a dry material, sodium chloride and calcium chloride are also used in brine. A brine is any solution of chloride and water. Most brine used on Iowa highways is made from a mixture of sodium chloride, rock salt, and water. A brine maker is basically a large container in which the salt and water can be mixed. Some Iowa DOT garages have pre-manufactured brine-making systems. Others have been built by Iowa DOT personnel. An important tool in brine making is a hydrometer. It is used to measure the specific gravity of a solution in water. For our purposes, it basically measures the percent concentration of salt in a brine solution. Most garages use a specialized salt brine hydrometer called a salimeter that converts the specific gravity into a salt concentration reading on a scale from 0 to 100%. The ideal concentration of salt in a fully saturated solution is 23.3% by weight. That equates to a salimeter reading of 85%. The salt solution concentration is critical in the production of brine because if the concentration is too low or too high, the brine will not do its intended job. In order to fully understand how de-icing chemicals do their work on roadways, let's review some basic physics and chemistry. If the H2O molecule, or as we know it, the water molecule, were visible, you'd see an oxygen atom with two hydrogen atoms attached. In this asymmetrical molecule, the two hydrogen atoms have a positive electrical charge, while the oxygen end of the molecule is negatively charged. In their gaseous state, water molecules move so fast they bounce off each other and never become attached. In their liquid state, water molecules are moving too fast to stay locked into crystals, but slowly enough to be attached to each other. In their frozen state, or as ice, water molecules are locked together in six-sided or hexagonal crystals. Individual molecules are vibrating, but they aren't going fast enough to break out of the crystal. The attraction of the positive hydrogen atoms of one molecule to the negative oxygen atom of another holds the crystal together. Now that we understand how water turns to ice, we can better understand how de-icing chemicals destroy ice crystals. This is what the salt or sodium chloride molecule looks like. It is made up of one positive charged sodium ion and one negative charged chloride ion. When salt is applied to the ice and there is moisture or water present, the sodium chloride molecule begins to break apart into positively charged sodium and negatively charged chloride ions. The negatively charged oxygen atoms of water are attracted to the positive sodium ions in the salt. The positively charged hydrogen atoms of water are attracted to the negative chloride ions in salt. Because water molecules are more strongly attracted to sodium and chloride than to each other, they unlock from their ice crystal formation even at temperatures below 32 degrees Fahrenheit, when in the presence of the sodium and chloride ions. This attraction destroys the structure of the ice crystal and dissolves the salt, resulting in a liquid salt and water solution, or brine. Therefore, de-icing and anti-icing chemicals like sodium chloride work by lowering the freezing point of water. The actual freeze point of a solution is governed by the concentration of salt in that solution. This is illustrated by this phase diagram, which has temperature on the vertical axis at the left and the solution concentration percentage for sodium chloride along the horizontal axis at the bottom. The diagram shows the temperature at which various concentrations of brine change phase, from liquid to solid or freeze. For example, at 20 degrees, a 10% solution of sodium chloride could melt ice. The freezing point continues to decline down to a -6 degrees when the concentration reaches 23.3%. This is what's called the eutectic temperature of sodium chloride. -6 degrees is its maximum freezing point depression. Note that as the concentration increases beyond 23.3%, the freezing point of the liquid chemical rapidly increases. This ability to lower the freezing point of water is a unique feature of de-icing chemicals, and each de-icing chemical has its own special characteristics. The eutectic temperature of calcium chloride, on the other hand, is -60 degrees. A 29.8% solution of calcium chloride doesn't freeze until it reaches a -60 degrees. It is this freezing point depression characteristic that makes de-icing chemicals so useful, and why sodium chloride and calcium chloride are called freeze point depressants, because they depress the freezing point temperature of water. Antifreeze in your vehicle is also a freeze point depressant. As we all know, water freezes at 32 degrees Fahrenheit. Straight antifreeze freezes at 2 degrees. However, when you mix 50% antifreeze with 50% water, the freeze point temperature of the mixture is lowered to minus 35 degrees. Like antifreeze, de-icers are less effective when too little or too much is used. The phase diagram best illustrates this and provides important principles that come into play every time you are out on the highway applying rock salt or brine. Anytime you apply salt, and the combination of solution concentration on the roadway and road temperatures fall into this green area, you have applied the right amount of chemical and the melting of ice will take place. If the combination of solution concentration and temperature are in the red area, ice is going to form because the solution concentration is not high enough to melt all of the ice. If the combination of temperature and solution concentration falls into the blue area, the material you apply will have no effect until more moisture is present to dilute the concentration. In the yellow area, below minus 6 degrees, melting will not take place at all. The salt will sit on top of the ice, no matter how much salt you apply, until the pavement temperature warms. The phase diagram also provides an understanding of how de-icing and refreezing can occur on a pavement. Let's say you apply brine to an ice-covered pavement that is 20 degrees. As long as the temperature remains at 20 degrees and the brine concentration is 23.3%, you are in the green area, and melting is going to occur. However, as the ice melts, the brine is diluted, and as soon as the concentration percentage drops below 10%, you begin moving into the red area, and the melted ice will begin to refreeze. Even if brine concentration remains high, let's say 20%, but the temperature begins to rapidly drop, you can see that refreezing will occur as soon as the pavement temperature hits 3 degrees. Take time to fully understand the phase diagram, because the principles it illustrates will come into play every time you are out on the highway applying de-icing chemicals. When a solid de-icer like salt is applied to an ice-covered pavement, it must first dissolve and become a solution before melting can occur. The moisture can come from pre-wetting the salt or from moisture on the highway. Calcium chloride, as we have learned, can draw moisture from the air to begin the melting process. However, too much moisture can rapidly slow or halt the melting process. Dilution of the solution quickly reduces melting power. Let's say you have just laid down 300 pounds of straight salt per lane mile, and there is a mere 0.02 of an inch of moisture on the roadway surface. The concentration of the salt solution present on the roadway will be 16.8%, and the freeze point will be 12.5 degrees. If just 0.03 of an inch of additional precipitation falls, bringing the total to 0.05 of an inch of moisture, the concentration drops nearly 10 percentage points to 7.17%, and the freeze point rises 12 degrees to just under 24 degrees. If you remember that salt brine at its most powerful concentration is a 23.3% solution by weight, you can see that dilution of de-icing chemicals can have a serious impact on their ability to melt ice. Dilution of solution always takes place as melting occurs or additional precipitation falls, whether it be in the form of rain or snow. Dilution of solution must always be considered when applying dry and liquid de-icing chemicals. In theory, you could calculate the exact amount of de-icing chemicals to apply if you knew the pavement temperature, the amount of ice the chemical must melt, and the amount of chemical that would stay on the roadway. However, changes in weather or traffic often alter those calculations considerably. The Iowa DOT has a variety of salt and sand spreaders. Most have spinners to spread material onto the roadway. Proper calibration of chemical application equipment is critical and must be done at least once a year for each mix you will be spreading. Whenever a spreader is worked on, it should also be recalibrated for each mix. Check with your supervisor on the method for calibration. When applying salt, The idea is to concentrate much of the chemical over the middle of the roadway so that as it begins the melting process, the melting liquid moves away from the crest of the roadway towards the outside. It is important to keep as much of the material on the roadway as possible. Traveling too fast or having the spinner moving too fast can result in more material on the shoulders and in the ditch than on the roadway. Low spinner speed is recommended to concentrate material on the highway. The only exception is when treating intersections. Use a higher spinner speed to spread material across the entire intersection. Refer to the calibration chart for truck speed and auger speed for proper application rates. Some trucks are now equipped with ground speed-oriented applicators, which automatically adjust to apply the same quantity of material, whatever the travel speed. As you have learned, the amount of salt that should be applied per lane mile can vary considerably, depending on many conditions: pavement temperature, whether temperatures are rising or falling, the amount of traffic, the type of precipitation forecast, and the roadway characteristics, whether it's a shaded cut along a grove of trees or a curve. Your supervisor will let you know what rate to apply or offer you advice, depending on the conditions. If you apply salt at the rate of 300 pounds per lane mile and it all stays on the roadway, a square foot of pavement may look something like this. Approximately 3 grains of salt, weighing 0.0047 pounds per square foot. At the rate of 100 pounds per lane mile, a square foot of pavement would have this amount of salt, about 1 grain weighing 0.0015 pounds per square foot. Even when you do an excellent job of placing salt on the roadway, traffic can quickly spread it out and off the highway. Using brine as a pre-wetting agent applied to the dry material at the spinner helps salt and sand stick to the roadway. Research in Michigan, comparing salt applied with and without pre-wetting, demonstrates the advantages of using a pre-wetting agent. These numbers show the percent of salt retrieved from a 24-foot pavement. On the center one-third of the highway, 78% of the pre-wetted material was retrieved as compared to only 46% of the salt applied dry. As would be expected, less of the pre-wetted material moved to the outside two-thirds of the pavement, 18% compared to 24% of the dry material. Only 4% of the pre-wetted material was not retrieved, compared to 30% of the dry material that disappeared off the highway. Visualize the amount of salt that does not stick to just this 1 square foot of highway if it is applied dry. 30% compared to only 4% if a pre-wetting agent is used. In addition to helping the salt stick to the highway, pre-wetting also helps jumpstart the melting action. As we learned earlier, moisture must be present for the melting action to begin. The only time that pre-wetting may not be required is when there is already plenty of moisture on the highway. Your supervisor can give you advice on the amount of pre-wetting agent to apply. In theory, when brine is used as a pre-wetting agent, the amount of dry materials can be reduced 20 to 30% because of the additional salt in the brine that is being applied and the fact that more material remains on the roadway. However, maintaining existing salt application levels with added pre-wetting will increase the melting process, resulting in a higher level of service. As we discussed earlier, anti-icing is a road maintenance strategy that tries to keep the bond between ice and pavement surface from forming. An anti-icing technique that has proven effective is the spreading of brine on the roadway before or at the very beginning of a storm. By applying brine prior to a precipitation event, it adheres to the surface of the roadway and is ready to go to work when the rain or snow begins to fall. This speeds up the entire melting process and also makes roadways easier to plow. Even if the forecast precipitation does not fall, most of the salt will remain on the roadway, ready to go to work when the next precipitation event occurs. Brine application rates can range from 25 to 60 gallons per lane mile, depending on conditions. Your supervisor will tell you what rate should be applied. When applying brine, Always be on the alert for rapidly declining pavement temperatures and rising winds. Be especially cautious when it looks like pavement temperatures will fall below 20 degrees and winds exceed 15 miles per hour. If it is 6 o'clock in the morning, the pavement temperature is 15 degrees and the forecast calls for snow to begin falling soon and pavement temperatures to reach 25 degrees by mid-morning, you are probably pretty safe in applying a brine solution. However, if it is 6 o'clock in the morning, the pavement temperature is 15 degrees and the forecast calls for snow to begin falling soon and pavement temperatures to remain stable or drop, you should reconsider applying a brine solution. One very important word of caution. Do not apply brine to packed snow or ice unless sufficient chemical is applied to achieve a wet pavement condition. Another caution when applying brine, especially calcium chloride brine. A dry residue can remain on the highway long after application. Under special conditions, especially if there is a great deal of moisture in the air, the calcium chloride remaining on the roadway will draw moisture to the road. And if the temperature drops, icy slick conditions can be created. The keys to applying brine as an anti-icer are accurate weather forecasts, knowing the pavement temperatures, and understanding the de-icing chemicals you are using.